We have already studied the PIC processor, its architecture, as well as its instruction set. But PIC microcontroller, other than processor, has also got on-chip peripherals. Today, we shall look at these peripherals. The more common peripherals on these PIC microcontroller family are digital I/O ports, analog to digital converters, serial communication interfaces like UART, SPI, I2C as well as CAN interface, pulse width modulation module, timers and counters, and definitely watchdog timer. It is not that all these peripherals are present in all PIC microcontroller variants. In fact, there are more peripherals than what are listed here present in some of these microcontrollers. But before going into these peripherals in detail, we shall like to look at interrupt mechanism of PIC processors, because these peripherals can be interfaced using this interrupt driven I/O with the PIC processor. First, we can have a brief review of interrupt. What happens when interrupt occurs? The CPU stops its current execution and it starts execution from a different instruction stream which is targeted for handling the interrupt. And when CPU finishes the interrupt, the execution returns to the original program. We shall see how this mechanism is really implemented in PIC. The sources of interrupt in PIC are many. Some of these sources are definitely the on-chip peripherals, but also there is a provision for external signals to interrupt PIC. There is an INT pin interrupt from external source, as well as there is another interesting source of interrupt which is called port B change interrupt. If there is a change in these pins, it can interrupt the processor. And rest, what I have listed are interrupts generated from on-chip peripherals. They are timer overflow interrupts, USRT interrupts. When there is a character waiting in the buffer to be read, there can be an interrupt. AD conversion interrupts. When analog to digital conversion is complete, there can be an interrupt. The LCD interface module can generate interrupts, and there are others also, because as we increase the number of peripherals on chips, we need a mechanism to control those peripherals, and they can also be source of interrupt for the PIC processor. And these interrupts are managed by use of few registers. Now let's look at the basic concept of maskable and non-maskable interrupts. If we have a maskable interrupt, it essentially means that I have a mechanism to enable or disable that interrupt. Also, another very interesting and important thing is concept of vector interrupt. When a vector interrupt occurs, the processor starts execution of the interrupt service routine from a fixed address. In fact, in PIC, we have only vector interrupts. The intcon register is used basically for managing majority of these interrupts. Also, there are other registers which are equally involved. I have listed the significance of the bits in the intcon register. The bit 7 is the most significant bit because it is global interrupt enable disable bit. And if we disable this bit, the PIC will not respond to any pending interrupt. Bit 6, 5, 4, 3 are for enabling, say, peripheral interrupts, timer 0 interrupts, external interrupt, and port B bit change interrupt respectively. In fact, when I enable peripheral interrupt, This corresponds to again another set of interrupts, because I can have many peripherals other than those which are listed here. For enabling or disabling those interrupts, I have a when interrupt occurs regardless of the value of the enable bit. If the enable bit is set, that means the interrupt is enabled, the interrupt is responded to. Otherwise, the interrupt may not be responded to, but the fact that interrupt has occurred would be recorded in the flag bit. For peripheral interrupts, what I said that once I enable peripheral interrupts, the source of peripheral interrupts can be various other peripherals, and I use the register called PIE, which contain bits for enabling interrupts from individual peripherals. Associated with PIE, there is PIR register, which contain flag bits for individual peripheral interrupts. And in fact, you can understand now again the utility of these bit oriented instructions that we have discussed in the previous class. Using those bit oriented instructions, I can enable or disable the interrupts. Also, I can figure out the source of interrupt by examining the flag bits of these registers. So, what shall I do to process an interrupt, or what a PIC is supposed to do to process an interrupt? When interrupt is responded to, the global interrupt enable bit is cleared to disable other interrupts. PC is pushed onto the stack. This is again a hardware stack, and now PC is loaded with a particular address, and this is the vector for the interrupt service routine. And what you are supposed to do in your interrupt service routine is to preserve a copy of status, at least the copy of status and W register. Why this is important? Because inside the interrupt service routine, if you do any processing that can affect W register, that will also affect the status register. And when you come back from the interrupt service routine to the main processing thread, you would like the original status and W to be restored back. So, while writing an interrupt service routine, you must save W and status register, if not other registers in some temporary locations. Inside the ISR, the source of interrupt is determined by polling the interrupt flag bit. Again here by using your bit check instructions. And when you return from the interrupt, you use ret fee instruction which we had already discussed. This causes the processor to exit from ISR and sets GIE bit, that is global interrupt enable bit, so that now processor can respond to pending interrupt. And this pending interrupt might have set the flags and should have set the flags, and again in the ISR you can check the flag to determine the interrupt. So, actually what you find here is that your interrupt handler routine for specific interrupts should be jumped to or called to based on the flag bit that has been set, and that flag bit is checked inside your interrupt service routine. So, let us look at the interrupt timing for PIC. Now, let us say that this is my basic clock, and this is your 4-phase clock which is controlling the entire processing of my PIC processor. We have discussed this clock in the context of instruction cycle also. Now, just consider that here what we are looking at is the source of external interrupt along INT pin. So, here when the interrupt is occurring, and what will happen? There would be a delay, and at that delay the INTF flag would be set. The flag is indicative of the source of the interrupt, and what is assumed here is your global interrupt enable flag is set. That means the processor is enabled to respond to your interrupt. Now, the interesting feature is, that is the point I have got a rising edge of the INT pin to the point where the first instruction corresponding to ISR gets executed is typically your what is called interrupt latency. This is the hardware latency, okay, and this latency is the basic delay which is involved between the raising of the interrupt and that of servicing the interrupt. Now, what we will find here when we look at the instruction flow, at this point I was actually executing the instruction which was pointed to by PC here, and I had already fetched the next instruction because that is a basic pipelining in the PIC processor. But since interrupt has occurred, so what will PIC do? It has to respond to the interrupt and start execution of the instructions from ISR. So, you will find effectively a dummy cycle is introduced here, which I was referring to as NOP, nothing happens in that cycle. And in this cycle, what you do is, basically the instruction that you have actually fetched is not being used. So, instruction fetch is, there is a blank over there, and the PC is effectively set to the vector address. Now, you fetch the instruction here, and here also the execution wise it is still a dummy cycle because you have not got the instruction to execute. After this, at this point you start execution of the instruction from that vector location and you fetch the instruction from the next location. So, this is basically the interrupt latency, that is a delay behind the servicing. Okay. So, the time gap between the interrupt occurrence and the service which can be provided. Now, this is a very critical component, this interrupt latency, because this is a hardware latency and there would be also a software latency. These two things have to be taken into account while designing an application, because I need to satisfy interrupt constraints. What kind of constraints? Because I am making a system which is situated in the external world, and if we assume that there will be interrupts generated from the external source, I need to know the frequency with which the interrupt is expected to be generated. And so, each interrupt source, which may be an external source, or for the case of microcontrollers can be peripherals which are on chip, I need to characterize each of the source by the minimum time interval between interrupts and the maximum time it takes the CPU to execute interrupt sources handler. And what is interesting to note is that the first instruction in the ISR is not really the instruction of the interrupt sources handler, because I have to figure out the source by checking the flag bit and then only jump to the instructions which are supposed to service the source. And when I am inside an interrupt servicing routine, I am actually disabling the interrupt. So, if there are other interrupts occurring, they have to wait. So, when I am designing interrupt service routine, I have to be very careful to check what the maximum time that an interrupt service routine can take delaying other pending interrupts. And by delaying other pending interrupts, I should not miss a deadline imposed by the external world. And this is the key issue which goes into designing appropriate interrupt service routine. So, what is the basic bottom line? Servicing of interrupts must not be delayed beyond the limit imposed by the timing requirement of the source. So, when you are using an application and it is a dedicated application, so you know what are the sources of interrupt, what are their frequency, and accordingly you should design your code so that you do not miss the deadline. And this deadline is imposed by properties of the external source, and you have to design code to meet the deadline, taking account the instruction execution frequency as well as hardware latency. Next, we come to the concept of critical region. A critical region is a sequence of instructions, we have referred to that in the last class as well, is a sequence of instructions that must be protected from an intervening interrupt, or otherwise it may produce erroneous outputs. And in a PIC, this problem is handled in two ways. One is you have got a single cycle read, modify, write instructions. So, in this case you read, that means you are reading it as well as checking and modifying it in one cycle. So, after read there cannot be an interrupt, okay, before you really modify, that is changing the status. So, read, modify, write instructions help you to implement critical regions, particularly with reference to your external world and external inputs. Other thing is obvious, that if I disable my GIA bit over a range of code, I shall ensure a critical region. But at the same time, in this case I am increasing the interrupt delay. So, that constraint I have to keep in mind. Also, I have told you that we can also use a swap instruction to implement this kind of synchronizing primitives to ensure correctness of critical regions. So, with this background on interrupts, we shall now look at the different peripherals, because many of the peripherals would be interfaced or can be interfaced using this interrupt processing structure of PIC. The most common peripheral is digital I/O. All PICs have digital I/O pins and we call them as ports, and in fact there are external pins and these pins are associated with registers. So, whenever we want to do any manipulation on the port, one of the way of doing it is to read write these registers. So, ports typically are used to control and monitor external devices, and in fact to read input or write output onto the external devices, and each port has, I told you, two control registers. The trace X is the port identity. If I have port A, B, C, D, X will be replaced by A, B, C, D, sets whether each pin is an input or output pin, that is the direction of input output. Port X sets their output bit levels. Most pins have typically 25 milliamp source or sink, so that it can directly drive the LEDs. So, this is a typical configuration of port A. Okay. So, this is essentially your data latch. I am showing it for a single bit. So, when we look at it for 8 bits or multiple bits, there will be multiple such latches, and this is your trace latch, which actually records the status that you set. So, what we say, the setting a trace A bit, because I am referring to port A, put output drivers in high impedance state, and clearing a bit in trace A puts contents of output latch on the pin. When the output drivers are in high impedance state, I can use that pin as an input pin. Okay? And many cases, even these digital I/O pins, there are some cases where it can be configured to get even analog inputs for some other purpose, because these pins are multiplexed for serving requirements of other peripherals as well. So, this is the basic structure. You can see that these are the two latches which actually record the data as well as the trace bit, enabling the direction of operation. Let us look at the code. So, what is happening here? This is an example of a code for initialization of a port. So, typically we clear the status. Now, in this case obviously I am selecting the bank 0, because these ports are also located on banks, memory banks, so I have to select the bank. Then I am clearing the port A, this is the corresponding data latch, and then you are selecting the bank 1, okay, and using the bank 1 you are writing what? You are basically writing onto this trace A. Trace A is a control port which sets the direction of the pins on port A. Is this clear? So, once we write the appropriate data, so this has been now programmed as that bits 0 to 3 are programmed as input and 5, 4 as output. So, this can be done by writing onto trace A, and this is I am doing by selecting the appropriate port address along with the appropriate memory bank. So, this is a typical code to be used for initialization of a port. Now, there is another problem associated with the code. Let us look at this read, modify, write instructions enable us to implement the critical region, but there are also some issue involved here. Just imagine that you have read and then there is an external input which pulls a different output pin low or high during the read, because read takes some finite clock time. So, read in value will not be what you expect. Words, the write will permanently change it that way, okay, because after write the port these bit values would be changed and it would be changed permanently. So, this also can be source of problem and source of error when you are interfacing the external devices via port. So, one of the solution is that you use what is called shadowed I/O. That means you clear in this case basically when I am showing underscore port A, it is not that I am writing onto exactly the port A memory location, but a copy of port A memory location which is in general purpose set of registers which PIC provides for. And then what you do? You write onto a W and from W you write onto port A. So, here what is happening is you are actually reading the data and whatever manipulations you are doing on a shadow register. So, it is not being directly done on the port A register, only thing is that I am writing final result onto the port A register. Okay. So, intermediate result will not affect the operation that you are trying to do. Next we look at timers. Timers are very important peripherals for any microcontrollers, because timers are used for synchronization with other devices, taking care of various timing requirements for control applications. And there are a number of timers, in fact typically 3 timers on mid-range PIC microcontrollers. And what we say the 14 plus bit codes means what? When your instruction length is 14 bits, these codes enable the timers to generate interrupts on overflow. Some timers are 8 bits, some are 16 bits, and they have pre-scalers as well as post-scalers. In fact, not all of them have both, some of them have one of it, and they can have even both. And they can use external pins as clock in as well as clock out. So, it is not that all these timers are being operated by the internal phase clock, the processor clock. So, let us look at timer 0. This is an 8-bit timer with a prescaler. What is really a prescaler? Prescaler is basically an option for dividing the input, that is the input which is coming to the counter, by various factors. So, I can set the factors maybe 2, 4, 8, 16. So, if I have an 8-bit programmable prescaler, I can set a value to the prescaler. So, that would mean that input waveform is divided by that factor before it is being fed to the timer. So, effectively what I am doing, I am increasing the range over which and the time period over which the timer can really count. These timers are readable and writable. So, I can read the current count as well as I can write to modify it. And it can be set to internal or external clock, and in fact, you can see that external clock is connected to bit 4 of port A. So, this is an example what I had already told you, that these bits, I/O bits, are multiplexed for various tasks with peripherals. This is an example where bit 4 of port A can be used as a external clock for the timer 0, and it generates interrupt on overflow. Then we have got another timer. Now this is timer 1, this is a 16-bit timer. Okay. Now this 16-bit timer counter can also generate interrupts on overflow, just like it is other timer readable and writable. It has got a programmable prescaler, but what is interesting is it can operate in different operating modes. It can operate as a synchronized timer, it can operate as a synchronized counter, it can operate as an asynchronous counter. Now there is a basic difference between them, and these differences are interesting. A synchronized counter, when it works as a synchronized timer, not counter, it increments every instruction cycle. That when it is perfectly synchronized with the processor clock, and you can count the number of instructions that is getting executed using this timer. It can also be used as a synchronized counter, and in this case the timer increments on rising edge of external clock. But this external clock is synchronized with internal phase clock. So what does that mean? It means that if we put somehow the internal phase clock off, then it will no longer count, because it is synchronized with the internal phase clock. So if the phase clock is off, it cannot count. The other mode is asynchronous counter. The timer increments independent of internal phase clock. So I can feed it from an external source and it would continue to increment independent of the external phase clock. Now this is a typical application of a timer. I can build a real time clock using this timer, and this timer operating in a asynchronous mode. Because in an asynchronous mode, just look at it, in an asynchronous mode the timer needs to count, and I can actually put my processor to sleep. If my processor is not doing anything, if you have designed just a digital clock to display the time and do some other task, but that is an occasional task, and you may use the processor to do user interaction. So in the majority of the time I can put the processor to sleep. Okay? The moment I am putting the processor to sleep, I am saving on energy. Okay? And since it is an asynchronous clock, it can operate from an external source of external clock signal. Okay? So timer continues to count, and when it overflows, it wakes up the processor. Once it wakes up the processor, now processor can do what? Can update the display. Okay, this is an LCD display, and I told you that many of these PIC microcontrollers do have LCD interface module. So using that LCD interface module, I can connect an LCD and I can update the display on the LCD. So the processor is not doing anything normally. It just wakes up on getting the interrupt, okay, on timer overflow, and updates the display. And the timer works on its own from an external clock source. So I can connect external crystal as well to this timer. In fact, what I have shown here is that we have connected an external crystal. These are the inputs to that timer 1. Okay? And this can be the keypad interface for an user interaction with that clock. In fact, this you can consider to be a very simple embedded system built around your PIC. There is another timer, it is called timer 2, and timer 2 is readable and writable 8-bit counter with both prescaler and postscaler. Now here we have shown its configuration. In fact, whenever we are using prescaler or postscaler, this is the basic structure. So what do you find? That the input here, I can set these different values to the prescaler. So that means this will divide the input when it is being fed to the timer. And a postscaler means what? So postscaler also can be set to different values for post scaling the output of the timer 2. And these bits that we are showing here, these are some of these control bits which can be set to set the different values to the prescaler as well as a postscaler. And in fact, this timer has got a very interesting property we shall see soon, and we have just shown that property here, a glimpse of that property, but not exactly how it is used in the complete context. See, we have shown here a PR2 register, that is some register we can set. So, if I set a value to this register, this is a comparator which can actually compare the timer value with that of the preset value, and if it is equal, I can possibly reset the timer, okay, and I can change the value depending on the requirements, and I can reset the timer on the fly, okay. So, you can see this kind of a functionality is provided with timer 2. So, you can realize that although I am discussing 3 timers, a very basic question can come, why 3 timers, why not 1 timer? You can see that these 3 timers perform and play different roles because of the different functionalities, okay. So, and these timers, that is why have been provided on chip on some of these microcontrollers, that is PIC microcontrollers, to take care of different requirements. Along with the timer, there is this watchdog timer, which I told you is a very important component for majority of microcontrollers. Why it is important? Because when the microcontroller goes into some kind of an undefined state because of a software error or an hardware error, you need some mechanism to come out of that error state, and this watchdog timer provides that facility. So, it is a free running on chip RC oscillator provides the input for this timer, and it does not really require an external component as a clock source, and timeout generates a device reset. So, the device is reset to the initial state. In sleep mode, a WT timeout causes the device to wake up, that when the device is sleeping, if this timeout causes, the device will wake up and it will start processing. And what you have to do is, to avoid unintended device reset, we need to clear the watchdog timer. So, I have already talked about the clearing watchdog timer instructions, and I can also associate the post scaler. By using the post scaler, I can vary this time period, okay, because after, what will be the time period after which watchdog timer should generate a timeout? That can be programmed through your this post scaler. And when you, by setting the post scaler, you can change the period. So, by clearing the watchdog timer and setting the post scaler, you can avoid unintended device reset. Another interesting feature is, I talked about, if you remember, there is a configuration port on the processor, and in the context of this assembler, I said that you have to also specify the configuration property, so that when you are doing the software development, the system knows what is the configuration in which the processor is set. So, one of the bit in the configuration port, we shall not have time to go into details of it. One of the port is, one of the bit in that register is targeted for enabling or disabling the watchdog timer. So, if I disable the watchdog timer, then all these things are of no consequence. Next, we shall look at another module which is called CCP module, Capture Compare PWM module. There may be one or more such modules on this PIC microcontroller, and this is again targeted for various kinds of control applications. Each of these module contains a 16-bit register which can operate as what we call 16-bit capture register, 16-bit compare register, or as 10-bit PWM master save duty cycle register. And capture counts external pin changes, and compare will interrupt when the timer equals the value of a compare register. Now, what is PWM? Pulse width modulation, and we shall see also its application, how it happens. First, let us look at the capture. Capture mode records value of timer 1 when events like rising edge or falling edge occurs on pin CCPX. CCPX means, depending on the number of CCP modules you have, it will be CCP1, CCP2 external, etc. When capture is made, what happens? Interrupt request flag is set. In fact, it can lead to generate, this is one of the source of peripheral interrupt. Now, this is a very interesting feature. What you are doing? That you are actually recording events, and you are recording events with respect to time. This kind of feature is not commonly available in other processors. Okay, you have not found, you have not, must not have encountered them when you look at a general purpose processor like 8085 or 8086. And it is provided on this because it is supposed to take care of various external events interfaced with the external world. So, it can actually keep track not only of the event, but also the time, in a sense relative time based on the timer count when that event has occurred, and that value is recorded in the capture register. Then we have got a compare. The content of register is compared with timer 1 register pair value. When match occurs, the voltage level at CCPX pin is changed depending on the value of control bits. In fact, it can be I can have a rising edge, I can have a falling edge, there may not be any change. So, I can program what happens when the comparison takes place, okay, and when comparison is giving you equality as a value. Okay. So, the interesting feature here, you can realize that you can generate also through this process external signals. Okay. Not only just I can possibly match and reset my timer, but not only that, I can also generate an external signal to control an external device by taking care of this feature. So, that CCP module in that way is distinct from other kind of peripherals which you commonly encounter. Next, we shall look at the P part of it, that is your pulse width modulation feature of the CCP module. Now, what is pulse width modulation? All of us know that I can change in a very simple fashion, I can change the duty cycle of a square wave, and that is precisely what we are doing when we say that we are modulating the pulse width. And this duty cycle is expressed typically as a percentage of the total period. And if we change this duty cycle, what will happen? The average DC voltage would change. So, what we can look at it and thought of as average DC voltage will be approximately the same percentage of the on voltage. And I can do more elaborate and actual calculations, but conceptually the picture is like this, that average DC voltage will be approximately the same percentage of the on voltage. So, now I can use this concept for intensity control. By changing the DC voltage, I can control the intensity of a light source. I can do a DC motor control, I can do a temperature control, that is controlling an heating element, and what I shall do in that process, I shall just change the duty cycle, and I need therefore on chip in hardware facility to control the duty cycle as well as period of this PWM, and that is exactly what the CCP module provides for. So, what we say that in pulse width modulation mode, the CCPX pin produces up to a 10-bit resolution PWM output. Since CCPX is multiplexed with the port data latch, the corresponding trace bit must be cleared. This is again another point that of multiplexing of the pins I talked about. And typically your PWM module is coupled with timer 2, and period and duty cycle of timer 2 output is manipulated for obtaining the desired PWM waveform. And this is again another important role that timer 2 plays in PIC. So, how it happens? Let us look at this. Now, what you have got? This is your timer, okay, and this is your timer 2, and this timer 2 can be compared with this peer 2, that is, and by that I can control the period, okay. And what happens is here using this comparator I can control basically the duty cycle, okay. So, what we are talking about here is the duty cycle register. So, I can control the duty cycle, okay, by through this part of the circuitry, and I can control the period also through this part of this circuitry. And using this, what happens is I provide the output, and I provide the output on the one of these IO pins, and effectively I have to set my tree speed appropriately so that I get the output on that pin. So, what are the steps involved therefore for setting up a PWM? the steps required is establish the PWM period by writing to PR2 register, because I have shown you that when I do the comparison, that comparison would take care of the period requirement of the PWM waveform. Establish the PWM duty cycle by writing on to these two bits. We have to make CCPX pin as an output. We need to establish the TMR2 prescale value and enable the timer by writing on to T2 con. In fact, this we are talking about a timer 2. In fact, all the timers have got a enable bit which we can set by one of these bits which have to be set to enable the timer, and configure your CCP module for PWM operation. So, if we go back to the previous slide, we can see that what we are talking about? We are talking about setting the duty cycle, setting the PR2 for determining the period, and what we have not shown the prescalers. So, we have to set the prescaler and to get the PWM in the waveform. So, once we set it up, we get the PWM in the correct form. So, what does that mean effectively? If we now look at this application of controlling a DC motor, effectively the speed of the motor would depend on this ratio of T high and T low. So, that means when you want to change the speed, what do you need to change? I can change, if I want to keep my period unchanged and change the duty cycle, I have to change the corresponding bits. If I change my duty cycle, my speed can also change, because average DC voltage would actually be more. This is a very simple way by which I can directly use the PIC microcontroller for a DC motor speed control applications. It can be used for a variety of other applications, as I have already told you, intensity control of a light source, temperature control of an heating element, so on and so forth. In fact, one of the applications, major application for which PIC was designed was control applications, and that is one of the reasons why you expect and you have got the CCP module on chip of PIC. There are other PIC peripherals. A very common PIC peripheral is analog to digital converters. So, which converts your analog input to 8-bit or 10-bit digital value. And here these analog to digital converters are typically successive approximation ADCs. You can select your input analog channel, your conversion clock, as well as analog reference voltage in a software selectable fashion. Now, interesting feature is this ADC can operate even when device is in sleep mode, and once the conversion is over, the ADC generates an interrupt and it writes the result onto a special register which is called address register, not address register, address register, where the result is put in. So, this gives you a kind of a flexibility on it. Typically, it was 8-bit as well as your 10-bit ADCs are available. Now, the reason for providing ADCs are interfacing with external analog inputs. Many of your external sensory inputs would be analog. Once we get the analog input, we actually convert into digital form for doing any further processing. There is another module which is called synchronous serial port module. Now, what is this? This module is primarily targeted for, this is SPI module. In fact, this can be used for setting up your SPI as well as integrated circuit interfaces. In fact, these two are specifications of buses by which you connect other devices as well as other microcontrollers to your microcontroller. So, in a sense, these are bus interface modules, and we shall not discuss much about it here. We shall discuss it later on when we talk about interfacing devices to the microcontrollers, because what we have discussed really is till now is the peripherals which are on chip, and how these peripherals, on chip peripherals, can be interfaced and used by the processor. And this module, this is again an on chip module which provides you a mechanism for connecting other peripherals and other processor with your microcontroller. There are other PIC peripherals, okay, what we have discussed so far. Now, one is 8-bit parallel slave port, okay. Now, if you look at your digital I/O pins or the ports that we have discussed, what is the difference with them? Difference is they are actually, we have considered and we have used them as a single bit, I/O ports, okay. We can actually manipulate, I can set individual bits to be either in input or output mode separately, and I can read them. Now, what we are talking about here is a 8-bit parallel port, and typically for interfacing with 8-bit peripherals or microprocessors. And there these ports are typically multiplexed onto one of the device's I/O ports. Now, why this kind of a port is at all required? Simply because there are lots of peripheral chips which are available in the market which were targeted for interfacing with 8-bit microprocessors, and the PIC wanted to have a facility to use them as well. So, this 8-bit multiplexer parallel port provides for that. There is also an USRT module which is universal synchronous and asynchronous receiver transmitter module. It can be configured as a full duplex channel for communication with peripheral devices like CRT. In fact, CRT or PC you can communicate through USRT. So, in fact, this USRT is essentially implements your RS-232C protocol, which is typically you find with most of your serial interfaces on the PC or other devices. It also has got an LCD module. The LCD module requires what? A mechanism to time, to do a timing control for the purpose of display. So, it provides an interface for the timing control and also provides the control of actual pixel data, because whatever data which is being written onto the pixel, how it is to be written onto, and this pixel data would map to a memory area. So, that LCD module has provision for this timing control as well as management of pixel data. So, in fact, the example that I had already shown you, the clock, that means a real time clock you can implement by picking up a simple PIC and interfacing a LCD module and putting in a crystal, and obviously by writing an appropriate software and loading that appropriate software onto the PIC. You really do not need any other components. The another interesting PIC peripheral is that of EEPROM, that electrically erasable PROM data memory. Okay. Now, so far we have seen data memory and discussed data memory as registers which were RAM area. Now, we are talking about electrically erasable. In fact, this provides you a facility for storing the data even when the power is out, or in some cases you have not operated the system and you want to record the status for subsequent debugging, so on and so forth. Now, these registers are readable and writable under normal conditions. What do we really mean by normal conditions? Normal conditions means under normal supply voltage, DC voltage conditions, you can access these locations. You do not require any other supply voltage for accessing these locations. But these locations are not mapped directly in register file space, and what you need, you actually would be using indirect addressing. There would be a specific register, okay, onto which you will be writing the address, and that register is again a special function register. If you remember, I said that PIC has got both general purpose registers as well as special function registers. So, this will be one such special function registers, and you will be using indirect addressing to access these memory locations. So, if you want to record some data, you will be using these locations to record and store that data. Also, the higher versions of your PIC microcontrollers have got in-circuit programmer. Now, serial in-circuit programming support. Now, this is interesting and important because when you are developing a software, okay, you are developing a software, and we can assume that you will be developing a software either in assembly language or even in C high level language, and you translate that to assembly and finally to the machine code. And your program area is either EEPROM, okay, or it's a flash. Now, you need a mechanism to load your program onto the program memory area. So, this serial in-circuit programmer provides you with that facility. It provides a serial interface by which once you have tested the program in a simulation environment, maybe on your host platform, you can load your application onto PIC and you can execute that application on PIC itself. So, obviously, it reduces that once I have in-circuit programmer facility on the chip itself, it reduces what we call time to market. It is not that I have to develop the software and give it to the manufacturer to pre-program it onto the processor. I can get the chips onto my site. I know I have got the software tested and I shall just program it on a production line and get the output product. So, that reduces the time to market, reduces or also increases the flexibility of usage of these PIC microcontrollers. In fact, I have told you that when I use flash version, that is also another advantage. So, now I told you what I have told you so far is a general description about the PIC processors, its instruction set and the peripherals. Now, we shall just look at some specific examples of PIC microcontrollers. A low end example is 12C508, okay, and you see that there is a restricted set of features that we have so far discussed. Not all the features are present here because it is targeted for low end applications and it will have low cost. So, it has got a 512 only 12-bit program memory. It operates at 4 megahertz. It has not got 35 instructions, but 33 instructions. It is typically an 8-pin package. It has got 5 GPIO pins and interestingly only 2 level hardware stack, no interrupts, okay. And it has got peripherals, simply timer and watchdog timer. Watchdog timer should be there to recover and the timer for a simple application. So, for a very simple application, you can use this PIC. Okay, so, you can, the interesting feature is using this basic architecture feature, you can get a variety of processors. Okay. Conceptually, all these processors support similar instruction set, similar architectural feature and similar way of interfacing with the peripherals. Only the set of peripherals as well as the repertoire of instructions, the data size, data memory size as well as the program memory size changes. The other one is a mid-range, which is a bigger one, and in fact, our discussions had been primarily centered around this mid-range PIC processor. Okay. So, it has got operating frequency 20 megahertz, it has got 35 instructions, it has got 14-bit instruction set, it is also flash, so that program can be updated on the fly. It has got 8 level hardware stack, it has got electrically erasable PROM, that this data register that I had already talked about. It has got 10-bit ADCs, it has got 22 general purpose IO lines, the port A, port B IO lines that I was discussing. It has got USRT, it has got SPI, I2C, all these peripheral interfacing, serial interfacing mechanisms that I talked about. It has got both 16-bit and 8-bit timers, as well as it has got brownout detect and in-circuit debugger. What is brownout detect? When there is a voltage level fluctuation, one is power out, when is power out I go to the reset state. Brownout detect is that when there is a voltage level fluctuations, I can detect that and I can go to a predetermined state. So, this finishes our discussions of PIC family of processors. we have discussed architecture, instructions as well as peripherals. And PIC processors are well suited for low end and mid range applications. In the next class, we shall look at 32-bit processor which are targeted for primarily high end applications.